Okay, class, welcome back. Today we're going to talk about gases and how we can use gas laws to relate volume, pressure, temperature, and moles together. If we could summarize our objective for today into one sentence, it would be that we would be able to use the three simple gas laws to mathematically solve for our final or initial volume, temperature, pressure, or number of moles. Okay, with that being said, let's dive into gases. To start lecture off, we can survive weeks without food, days without water, but yet we can only survive a few minutes without air. Through respiration, we inhale gases such as oxygen, in which we utilize for bodily functions, and then we exhale waste products such as carbon dioxide. These gases play a pivotal role in our abilities to function daily, but up till now, your background in the operations and behaviors of these gases have been very simplified. Today we're going to start broadening our understanding of gases and how they behave. We know that gas particles contain the highest amount of kinetic energy. As kinetic energy implies, this is the energy particles gain as they exert forces due to their freedom of movement. The faster the gas molecule moves, the more force they can exert on other molecules or surfaces. A good illustration of this is throwing a tennis ball at a wall. The harder you throw the ball against the wall, the faster and further it is going to bounce off the wall. This understanding brings us to our first term we are going to need to understand when it comes to gases, and it is pressure. Pressure is the force exerted per unit area. The total pressure exerted on a gas depends on several factors, including the concentration of all the gas molecules within that specific gas. The higher the concentration of those gas molecules, the higher the likelihood that those molecules are going to collide with each other, or a surface that results in a greater exertion of pressure. Pressure can be measured in several units. Millimeters of mercury, or mmHg, is the first unit we are going to talk about. We measure millimeters of mercury by placing a tube in a liquid, then creating a vacuum in that tube. This vacuum will then cause the liquid to rise up within the tube. Because mercury is significantly denser in water, it is commonly used as the liquid of choice in these barometers. Our second unit is the torr. Torrs are simply the amount of pressure it takes to move mercury up 1 millimeter in a barometer. So this can be thought of as 1 millimeter of mercury equals 1 torr. Our third unit of measurement of gas pressure is the atmosphere. An atmosphere is the average pressure at sea level. Since at sea level the average pressure on a barometer reads 760 millimeters of mercury, then we can assume that 1 atmosphere equals 760 millimeters of mercury. Another common unit of measurement for pressure is the Pascal, or PA. A Pascal is considered 1 Newton per square meter. As confusing as that sounds, all you need to know is how to convert pascals into other units of pressure. Our conversion factors for Pascal is its relationship to an atmosphere. So 1 atmosphere equals 101,325 pascals. Our final unit of measurement for pressure is the pounds per square inch, or PSI. 1 atmosphere equals 14.7 pounds per square inch. Now that we've got that background information out of the way, how then are we going to use this in our class? Well, there are 4 basic properties of gases that are interrelated. These properties are pressure, volume, temperature, and moles. We are going to use gas laws to explain how these properties are interrelated. For example, we are going to explain how a gas's volume varies with temperature at a constant pressure. There are 3 main gas laws, or 3 simple gas laws that we're going to go over today. Our first one is going to be Boyle's law. Boyle's law follows the idea that pressure results from the collision of gas particles with the walls of a container it is in. If the volume of the gas is decreased, the same number of gas particles become crowded into a smaller volume, resulting in more collisions with the walls and therefore an increase in pressure. We can use Boyle's law to calculate the volume of a gas following a pressure change, or the pressure of a gas following a change in volume, as long as temperature and a number of gas molecules remain constant. We represent this mathematically with the equation P1 times V1 equals P2 times V2. where P1 is our initial pressure, V1 is our initial volume, P2 is our final pressure, and V2 is our final volume. Now that we have that, let's work a practice problem with Boyle's law. A cylinder equipped with a movable piston has a volume of 7.25 liters under an applied pressure of 4.52 atmospheres. What is the volume of the cylinder if we decrease the applied pressure to 1.21 atmosphere? Okay, so first to solve this, let's fill in the information we know. We're given one volumetric reading and two atmospheric readings. This tells me that we are going to use Boyle's law. So P1 times V1 equals P2 times V2. We're given both our pressures in atmospheres, so let's fill them in first. So let's put 4.52 atmospheres in P1 and 1.21 atmospheres in P2. Our only volume given is our initial volume, so 7.25 liters which is now in V1. Now that we have all of our information filled in, we can rearrange the equation and solve for our missing variable, which is V2. This would result in P1 divided by P2 multiplied by V1, or 4.52 atmospheres divided by 1.21 atmospheres, and multiplying that by 7.25 liters. If we do the math outright, our new volume would be 27.1 liters, which makes sense because if volume and pressure are inversely related to each other, then if we decrease the atmospheric pressure of the gas, the amount of space that it would take up would then increase. Charles's law is our second law we are going to discuss. Charles's law deals with the relationship between the volume of a gas and the temperature of it. It states that temperature and volume are directly proportional to each other as long as pressure and the number of moles of that gas remains constant. So, when the temperature of the gas sample increases, the gas particles are going to move faster and collisions with the wall of the container or other particles become more frequent, and the force exerted on each collision is greater. So the only way for the pressure to remain constant in this container is for the volume of that container in which the gas is in is increased. Our equation for Charles' law is V1 divided by T1 equals V2 divided by T2. In other words, our initial volume divided by our initial temperature equals our final volume divided by our final temperature. Some key notes that we need to address before working a practice problem is that temperature in these types of problems are always expressed in Kelvin. To convert from Celsius to degrees Kelvin, we're going to have to add 273.15 to our degrees Celsius reading. Also, we must realize with these problems that the number of moles of the gas and the pressure of the gas must remain constant. Now, let's look at our example problem. A sample of gas has a volume of 2.8 liters at an unknown temperature. When the sample is submerged in an ice bath whose temperature is 0 degrees Celsius, its volume decreases to 2.57 liters. What was the initial temperature of the gas? So we see that this problem is dealing with temperature and volume, so it tells us that we are going to be dealing with a Charles' law problem. This means our formula is V1 divided by T1 equals V2 divided by T2. In order to fill our information in our formula, we must first convert our degrees Celsius to degrees Kelvin. So 0 degrees Celsius plus 273.15 equals 273.15 degrees Kelvin. And this is going to be our T2. Our initial volume was 2.8 liters and our final volume was 2.57 liters. Now we are going to rearrange our formulas so that we can get our remaining unknown, which is our initial temperature by itself. So our formula should read T1 equals 2.8 liters divided by 2.57 liters multiplied by 273.15 degrees Kelvin. If we solve for this formula, we should get 297.6 degrees Kelvin as our initial temperature. Our final gas law that we are going to talk about is Avogadro's law. So we have learned the relationship between volume and pressure in Boyle's law and volume and temperature with Charles's law. Now we're going to see the relationship between volume of a gas and the number of moles that are of that gas in a given container. Avogadro's law states that the relationship between the volume and the amount of moles of the gas is linear. In other words, as the amount of gas increases, the volume of the gas is also going to increase. You experience Avogadro's law when you inflate a balloon. With each breath you exhale, you add more gas particles to the balloon, causing the balloon to increase in volume. This only occurs as long as the pressure and temperature remains constant. Avogadro's law's formula is V1 divided by N1, which equals V2 divided by N2, or in other words, our initial volume divided by our initial number of moles of that gas equals our final volume divided by our final number of moles of that gas. Now, let's end this video by working an example problem of Avogadro's law. Let's say a 4.65 liter sample of helium gas contains 0.225 moles of helium. How many additional moles of helium must be added to the sample to obtain 6.48 liters of gas? All this is assuming that temperature and pressures remain constant. The fact that we are given volume in moles indicates that we are using Avogadro's law, so V1 divided by N1 equals V2 divided by N2. We are going to need to solve for how many moles of our gas we have after this change. To do this, we're going to rearrange our equation to say N2, or final amount of moles, equals V2 divided by V1, or final volume divided by initial volume, times our initial number of moles, or N1. Once we fill in our known values, we get 6.48 liters divided by 4.65 liters multiplied by 0.225 moles. Once we do the math, we get 0.314 moles present. Notice the question asks how many more moles are added. So we must take our final amount of moles, which is 0.314 moles, and subtract our initial moles, which was 0.225 moles, from it. If we do this correctly, we should get that there were 0.089 moles added to this system, or 0.089 moles of helium added to this system. Okay, that's all we need to cover today. Remember, these gas laws give us the relationship between volume of a gas and either the pressure, temperature, or number of moles of that gas within a controlled system. I hope this helped you out, and keep up the good work in the class. See you next time.